So, let's begin. It was kind of a light homework assignment yesterday. So let's talk about what everybody thinks, how to prove the following theorem. The set of all collineations is a group. I asked you to prove this last night. So, first of all, let's just discuss what's necessary in order to demonstrate this. What do we have to do to show that a set of transformations is a group?
Inverse property.
Yeah, we have to show, so we had in class here, Zach said the inverse property. We have to show that this set of collineations satisfies all four of the properties that we went over yesterday. The inverse property, the closure property, the identity property, and the associative property. Okay, so first of all, let's, and you're right to say the inverse property because that's the hardest thing to show.
Is it?
Or it's like the least trivial thing to show. Not to say that it's hard, but it's the thing that takes a little more thought to say. Okay? So let's just verify the, let's save that for last.
But if we don't, we could say identity and not do it.
That's true, but, okay, let's start with the identity. It's almost trivial, right? Proof. The identity property. So, in other words, what we want to show is that iota is a collineation. Okay, well, what does iota do?
Into itself.
Essentially nothing, right? Let's just recall the definition where iota of p is just equal to p for all points p in the Cartesian plane, the standard model of the Euclidean plane. Okay? So this is a collineation, right? Because you take a line, we said this yesterday. We said this in words. You take a line, you do nothing to it, it remains a line. Okay? So the set of all collineations has the identity property. Okay? Let's discuss the closure property. That is to say, if we take two collineations and compose them, that should be a collineation as well, if we want to show that the set of all collineations is a group. Right? Okay, so let's take alpha and beta collineations. Then what we want to show that beta composed with alpha is a collineation. How do we go about this?
Take beta or alpha. And argue it basically.
I'm sorry, say that one more time.
You can basically take the working definition.
Yeah, I mean, basically we'll just take a line in the plane, right? Take a line, L, in the plane. Then we know that the image of L under alpha is a line, right? Since alpha is a collineation. And furthermore, if we take the image of alpha of L under beta, that must also be a line, since beta is a collineation as well. And this is just the definition of composition. It's a line, since beta is a collineation. Again, this is just like the proof that transformations are closed under composition. The properties of composed transformations inherit, or rather the composed transformation inherits the properties of both the components. Okay? Okay, so, associative. The associative property.
This should work just like the other one, right?
Yeah.
Because it was more about composition than about transformations.
Exactly. This is something I alluded to yesterday. Every subset of the group of transformations, every subset of the group of transformations has the associative property. And that's because the associative property has nothing to do with ensuring that you stay within the set. You take three things and that are in the set, and it's just about how they're related.
That's how the operation works.
Right. So, I'll ask you to verify this yourself. If you're not convinced by what I just said, verify that any subset of the group of transformations has the associative property. Okay? When I say verify this, there's not really much to say. I just want you to think about it and realize why it's true. Okay? So now we get to the thing that takes the most work, technically, which is the closure property.
No, the inverse property.
The inverse property, sorry. Yeah, we already talked about the closure property. Inverse property. Okay, that is to say, if we take a collineation, it's a transformation, so we can find its inverse. How do we guarantee that its inverse is, in fact, a collineation as well?
It helps align to a line. So in the reverse, it's mapping the image line to the pre-image line. It's still a line.
Okay, there's a subtlety here. So
Then it has to map back to the original. Just something, yeah, you just have to,
You have to be able to find a line that maps
right,
to a given line. Okay, so I know that might not have come across to everybody on Zoom.
it's subjective.
On lines,
Right.
that's the thing that we have to show. Okay? We have to show that a collineation is surjective on lines, quote unquote. Right? A collineation is a transformation, which is a mapping of points. I put that in air quotes because we haven't exactly built the notation or machinery to talk about the collection of lines altogether. But the spirit of what we want to do is show that for any given line in the plane, there exists a line in the plane that is mapped to our given line by alpha. I'm going to write this down. I'm just saying it in words first. Okay? That's why this actually takes a little bit of work. Okay, so. This is what we want to show. Well, I guess I should write that. We want to show. We want to show that given a line, L, there exists a line, M, such that alpha of M is equal to L. Okay? Word of caution here. This is an equality of sets. The image of M under alpha is equal to the set of points that lie on the line L. Okay? L and M are not points. I know this is, they're lowercase, so they're not points, right? Okay, so let me just note M and L are subsets of R2, not points. Okay? The amount of times that a point like this was glossed over in my undergraduate career really screwed me up.
I guess the way I don't use that is a lot of times I'll write it using set notation, like logic notation. Like the figures, parentheses, the...
Yeah, but that's, becomes cumbersome very quickly.
True. I mean, I don't even words in that, I mean.
Yeah, but I just want to point this out, that's all. Okay, so, how, Andrew, did you have a question or comment?
Yeah, actually, I was gonna put it in the chat, but I guess I'm kind of struggling to see like how a line could be in R2 as opposed to like a point. I'm assuming like a point would be. Does that make sense? Like if you have two numbers, are you like thinking of it in like vector form? Like how is that?
So remember, so let me write this. Hopefully this will clear things up. Recall, a line is a subset of R2 of the form it's the set of points in the plane such that we have AX plus BY plus C equal to 0 for
Got it.
Okay?
That makes sense. Yeah.
Yeah, I'm telling you, this caused me profound confusion for many years. Okay, so I'm glad you're asking. So when I write alpha of m, I'm looking at all the points in the plane that alpha maps all the points in m to. Okay? And that's what we want to do. We want to guarantee that for any line L, we can find a line, a set, such that the image of this set M under alpha is L. Okay? Okay, so now let's go about trying to construct M. Right? Let's do the deed that we set out to do. Okay. So, take any 2 points, P and Q, on the line L. Okay, I write it this way just to emphasize again that L is a set. P and Q on the line L. Then, since alpha is a transformation, there are unique points. R and S, sorry, capital S. So that alpha of R is equal to P and alpha of S is equal to Q. Right? Okay, now comes the real rub here. We have to apply to Euclid's axioms. Any 2 points in the plane, R and S, there must be a unique line through them. That's an axiom of Euclidean geometry. Okay? Unique. There is a unique line defined by R and S by the axioms of Euclid. Okay, side note. I have to admit, when I was preparing for class last night, preparing for this class, I realized that the textbook, I can't believe it took me so long to realize this, the textbook does not tell you what the axioms of Euclidean geometry are. Okay? So, today after class, I'm going to send out an announcement to the Wikipedia page. Just read the axioms, because we will refer to them time and again. Okay, and that's an entirely, a very interesting subject in its own right. But I'll just ask you to read those axioms. I'm not going to require you to know them offhand. I just want you to have seen them. Okay? But hopefully, this seems familiar. That 2 points in the plane define a line. Okay? So, since alpha is a collineation, this line defined by R and S has to be mapped to a line. And namely, since the image of R and the image of S lie on L, that line that's defined by R and S must be mapped to L.
So you're relying on the fact that we know it's certain amount of points, combining Euclid vectors and to show that it's a circular line, because the line can be defined by a finite number of points.
That's right.
Okay.
This is the key step. That there's a unique line that is defined by 2 points. Since alpha is a collineation, the line through R and S, let's call it M. I should write that down. Call it M, must be mapped to L. Okay, and again, this is a technically correct thing to say, but we don't really have the notation to make it precise. But what we're saying is that a collineation is surjective on lines. So I'll put that in quotation marks.
Well, then the analysis to extend that.
Sorry?
Is it fun having X analysis to extend that?
Right, so what we've shown is a collineation is surjective on lines. Okay. So, remember where we are, we're trying to show the inverse property for the set of all collineations. Okay? So since we've constructed a line M that maps the image of M under alpha is L.
You must always go with 2M.
Right. Let's just look at alpha inverse of L. And what we want to show is that this is equal to M. Right?
That's a definition.
Careful. Let's appeal to
With RNN, okay, yeah. Easy points.
what is L? It's the image of M. Alpha inverse of alpha of M is the same as alpha inverse composed with alpha of M. This is iota. Iota does nothing. Okay? I mean, you're not wrong.
This isn't there yet.
The intuition is right, but this is
Yeah.
the full explanation. Okay. Is everybody okay with that? Okay. So, all right. So, I also want to say, and we'll get to this later in the lecture today, I've had more than one student come to me with concerns about having to execute proofs in the homework or the exams. So, I want to clear the air about this now. The exams will be primarily computation-based. However, often a computation constitutes a proof. Okay? So I want to try to dispel this anxiety that I've experienced a lot with my students. It's like, oh, I don't know how to prove things. It's like, you know how to make computations. Computations constitute proof very often. Okay? So I'm going to make this thematic throughout the rest of the summer. Okay? So don't worry, is all I mean to say. Okay. So asked you to do for homework yesterday is to come up with 3 examples of a subset of the set of all transformations, the group of all transformations, which is not a subgroup, okay? So,
Just to be clear, this last end means that the set of combinations is a group.
yes, right. I guess I should say that. So, the set of all collineations is a group. Okay. It's important to come back to what we were originally saying. Thank you for that. Okay, so the other thing I asked you to do for homework last night was to come up with 3 examples of subsets of the group of all transformations which are not subgroups. Okay, so yesterday we said together in class that the empty set is such an example because it doesn't contain the identity. Right? It doesn't have the identity property. It trivially satisfies all the other properties, but it doesn't contain the identity. So, who can tell me another example? Yes?
Taking the group and removing any singular transformation that's not the identity transformation because it breaks the inner property.
Sure, that's great. Okay, so let's just say non-examples of transformation groups. So, let me repeat what Zach said. If we take any particular transformation and exclude it from the set of all transformations, that set is no longer a group, right? Because that transformation has an inverse, and the inverse of that inverse is no longer in our subset.
Unless it's higher than that, then it breaks the other one.
Right, yeah, you could exclude the identity transformation, but, well, actually what I said still holds because it's its own identity. Okay, so let's write that down. So, take any transformation, alpha, we'll just call the set of all transformations G here. Then G, when we take away alpha, okay, so this is another piece of notation people might not have seen. So this is G the set minus the set that consists of one element, alpha.
So intersect one.
That's another way to say it, yeah. Right, so we're just considering the set of all transformations except for alpha. Is the meaning of that. Okay, and this fails to be a group because alpha inverse has no inverse in G. Then alpha inverse, an element of our new set G minus alpha, has no inverse. That is to say, alpha inverse inverse equal to alpha is not an element of G minus alpha. Okay? Great. Somebody else tell me another example. Or I guess I should say non-example. Counter-example. Yeah, great. Jordan says a singleton that's not the identity. Thank alpha in G, the set of all transformations, and consider the set that is just alpha alone. Sorry, alpha not equal to iota. Of course, this is a subset of G. And again, this does not have the identity property, as long as we insist,
Or the inverse property.
or the inverse property. Associativity? Sure.
Or the closure property.
Nor the closure property. This fails spectacularly, right? Whereas the empty set satisfies everything but the identity property, this fails always. Good counterexample. The best counterexamples are the ones that fail the most spectacularly. Good. Okay, let's just take one more. Somebody else tell me one more. Okay, what do you think?
You can make it just a closure by taking away an element and its inverse, and then showing that you can construct that with a composition of two other ones.
Okay, say that a little slower.
If you take an element which is a composition of two other elements,
Okay, so we want to take beta composed with alpha in G. Yeah?
and you remove both beta composed alpha and inverse beta composed alpha, it doesn't meet closure.
Great. Then consider, this is good because we can use the notation again. Right? Then consider the subset G minus beta composed alpha and beta composed alpha inverse. This set fails to be closed.
That's the only one that fails, which is fine.
And that's the only thing that fails here. Good, unless of course beta composed alpha is the
Yeah,
Is iota.
beta is alpha inverse.
yeah, right. So yeah, it can fail different ways depending on what alpha and beta are, how they relate to one another. Okay. Good. Great example. Great, all together great counterexamples. Good job. Okay, so are there any other questions before we talk about today's material? Okay, then let's begin. Oh, I also had a number of people ask about the exams and practice material for the exams. So if you read the syllabus, you'll recall that the first exam is next Thursday. Tomorrow, I will release practice material.
Cover all the practice material?
No. Right. So, I understand that it is somewhat anxiety-inducing when what I've experienced is that it's somewhat anxiety-inducing if people don't have the review material at least a week beforehand. So I'll give it to you all, and then you can start working on it. And then the exam will cover everything that we do up through next Tuesday. Okay? So I'll send that out tomorrow after class. All right? So, on that note, now we're going to discuss an important type of transformation. And its importance is based in the fact that it helps us classify different types of transformation groups in terms of how many of this type of element it contains. Okay? This is chapter 2, section 2. being especially pedantic because we're just getting comfortable with the notation and everything. But now I'm going to make an explicit note of where we will stop being exactly as pedantic as we have been. We'll most often drop the composition symbol. Between composed transformations.
So it's the only operation we're allowed to use in the group.
I'm sorry.
It's the only operation in the group.
Since we're only considering transformation groups, this empty circle is the only group law that we'll ever consider.
So we consider adjacency our operation symbol, and then
Yeah. Yeah, so in other words, whereas over the past couple days we've written this is the same thing. This is why it becomes more important that we have a specific class of letters that we use to indicate transformations, right? Because say I have a composition of transformations operating on a line without the dot, this is unambiguous, right? This just means beta composed with alpha. Okay? Yeah, so, and let me just give you a quick view forward. Today is basically the end of us endlessly defining terminology and laying out notation. We'll pretty much use everything that we've done in these first 3 days consistently after that. Okay? So I know that this seems particularly dry in the beginning, but we just have to make sure that everybody is on the same footing, notationally and terminologically. Okay? Okay, so given this convention, the usual arithmetic of exponents applies. Okay? So that is to say, there's not really any good notation for alpha composed with alpha, composed with alpha, composed with alpha, which is some of the motivation for getting rid of the circles. So we can just write alpha to the n, right? That is to say, alpha to the n, we just interpret this as alpha composed with alpha, composed with alpha, composed with all the way up to n times. And conveniently, when I say the usual arithmetic of exponents, I also mean this applies to inverses. It's no mistake that we use the notation alpha to the negative 1 as notation for the inverse of alpha. That way, what we usually think of exponents as for natural numbers, real numbers, also applies to this operation of composition.
with iota as our identities.
Correct. Okay, so in other words, alpha to the negative n, how this is interpreted is alpha inverse to the n, which by applying what I just wrote over here is just alpha inverse composed with this self n times. Okay. So, furthermore, now you tell me what is alpha to the 0? Yes?
It's just iota.
It's just iota. Good. Iota is the identity of our transformation groups. Iota is always the identity of our transformation groups. And that's because for any transformation, we have iota composed with beta is equal to beta composed with iota is just equal to beta.
There's no betas in each of the iota.
I'm sorry?
There's no betas involved, it's just iota left. It's 0.
Say that one more
There's
time.
no betas involved, it's just iota left. So that's why the 0 exponent gives you.
Yeah, exactly. So this, if what I said is true, if the usual arithmetic of exponents applies, then we had better have this. Right? Okay. So, here's the theorem. And I think I'm at a high risk of repeating myself here, but that's okay. For alpha, beta, and gamma, elements of script G, a transformation group, we have the following. So, firstly, beta alpha is equal to gamma alpha implies that beta is equal to gamma. Call this right cancellation. Similarly, we can cancel on the left. That is to say, beta alpha is equal to beta gamma implies that alpha is equal to gamma. Left cancellation. Okay? So, thirdly, beta alpha is equal to alpha implies that beta is equal to iota. And fourthly, if we have beta alpha equal to iota, this implies that beta is equal to alpha inverse, and likewise alpha is equal to beta inverse. Okay? These last two parts of this theorem, 3 and 4, are stating the uniqueness of the identity transformation. It's the only thing that forces a product or a composition to be inverses of one another. Okay? And likewise, if anything acts trivially on some transformation alpha, it must be iota. Okay?
It acts like iota, it's iota.
Say again?
If it acts like iota, you just.
It's iota, yeah. Okay, so how do we deduce this implication?
Okay.
Well, what can I do?
Injectivity.
Say again?
Injectivity.
It sits a layer above that.
Right.
So, what do we know about a transformation group? We know that it has the inverse property. So we can compose the inverse of alpha to both sides of this. Okay? That is to say, beta alpha, alpha inverse is equal to, gamma alpha, alpha inverse. This implies that beta iota is equal to gamma iota. Iota is the identity. You can take it down to the level of what it does on points. Iota does nothing, and then you operate beta on that point. You get beta. Iota does nothing. You operate gamma on that point. You get whatever gamma does. So this implies that beta is equal to gamma. Okay, I'm not going to prove the rest of these four properties because it's the same type of thing. Okay, but this is it's useful. It's still useful. You have to hold yourself in two modes of thought at the same time when we talk about transformation groups. You want to think about the transformation as it is a mapping of the plane, but you also want to exploit the group structure. Okay? Notice this computation I made has nothing to do with what the transformations beta, alpha, and gamma do to the plane.
Just the fact that inverse because it's a group.
Right. We're just using the fact that because we said they're bijective, they form a group. So we can do this type of formal arithmetic to deduce properties that allow us to manipulate these mappings. Okay? Okay. So, here's another theorem. I'll just say, check the rest yourself. Here's another theorem. And I think this will illustrate the point I was trying to make earlier, that very often computation constitutes a proof. You know, it's not always that you have to write a paragraph. Often in mathematics, it's very helpful to explain your reasoning in words. And I hope that through the course, we'll build that skill. But it's also valid to express your thoughts via computation, very often in mathematics. Okay, so let's say in a transformation group, the inverse of a product the product of the inverses in reverse order. Reverse order. Okay, so let's take an arbitrary product of transformations in a transformation group. Alpha 1, alpha 2, alpha 3, alpha n. Okay? By closure, this is also a transformation. Okay? What's the inverse of this transformation? How do we get to iota? What can we compose?
You want to do
with
a
this?
order.
Yeah, we have to successively peel off each factor, each composed transformation. Okay? So in other words, right next to it, I'll put alpha n inverse, composed with alpha n minus 1 inverse. Alpha 2 inverse, alpha 1 inverse. Right? So, by closure, this is the transformation. By associativity, I can put parentheses around this any way I like. Right? So I'll put parentheses here, and then I get iota in the center. And then say I put iota with alpha sub n minus 1 inverse. Then I just get alpha sub n minus 1 inverse back. And then I'll put parentheses around the next pair. And I successively get rid of pairs until I'm just left with iota. Okay? So, to conclude in symbols, what do I write? I've constructed the inverse of this product. So what I say, therefore, the inverse of this product is just equal to the product of the inverses in reverse order. Right? Because I constructed some element of my transformation group that produced iota when I multiplied it by my product. Okay? Okay. So, some more definitions. Okay. If a group G has n elements, then G is finite. And has order n. Okay? Otherwise, G is infinite. This may seem somewhat confusing at first glance, but I'm just going to say it and then we'll discuss. Okay? So, if there exists a smallest positive integer n, so that alpha to the n is equal to iota. For some element alpha in the group G, then the element alpha is said to have order n. And sometimes we write the order in G of alpha is equal to n. Now, why did I say this might be confusing? Well, I just told you in part 1 that order is a property of a group. G, capital G. Now I seemingly have overloaded the terminology order. Why would I make such a brash decision? Well, you're going to tell me that tomorrow. There's a homework exercise in the book that addresses this specifically. Think about that while we move forward, though. There's a reason that I define order in 2 different ways, and it's because ultimately they coincide.
Like generation. Okay.
Exactly. And we'll make that definition soon. Of course, here I haven't finished yet. What if there is no such n? What if there is no such smallest positive integer n, such that alpha to the n is equal to iota? Yeah, great. If no such n exists, then the order of alpha is infinite. And some abuse of notation, you will see this written certain places. Okay? I know I'm not a particular fan of that, but
Oh, equating to infinity?
yeah. It's okay. It's okay though. It doesn't bother me that much. Okay, let's talk about a couple examples. So, let's let rho be rotation by 360 divided by n degrees about the origin. Then the order of rho is equal to what? N. Yeah. means rho is a 90-degree rotation. So I rotate 90 degrees once, I rotate 90 degrees twice, I rotate 90 degrees 3 times, I rotate 90 degrees 4 times, and I'm back exactly where I started. Okay? Yeah. So, let me ask you this. Let's set tau of x comma y equal to x plus 1 comma y. Then the order of tau is equal to what? Heard some murmurs. Anybody on Zoom want to say anything? Yeah, good. This matches the murmur. Spencer says it's infinite. Right? Again, here's my plan. I apply tau, I move over 1. I apply tau, I move over 1. I can keep moving over 1, and I'll never get back to where I started. Okay, right. So the point is, it's nice when things have finite order, but even very simple things have infinite order. It's not that pathological of a behavior. Many transformations have infinite order. Okay? Okay. So, now we're going to talk a little bit about specific types of groups in general, and then we'll talk more about the transformation group, examples of those types of groups, okay? So, let's say this following definition. If every element of a group G is a power of some element alpha, then we say group G, we say G is cyclic and has generator alpha. And has generator alpha. We often write G is equal to angle brackets alpha. Oh, sorry. So Anirudh asks, are we assuming n in example 1 is an integer? Yes. Sorry, I should have said that. Here, n is an integer. I guess I should even say positive integer. Well, actually, it's okay. We can make negative.
Non-zero integer.
Non-zero integer. Not equal to 0. Yeah, good. Keep me honest. Okay. So, this is to say, essentially, everything about the group G is determined by alpha. We know everything about the group G, we know all the elements in G, just by taking powers of alpha. Okay? So, let's discuss a couple more examples. Okay, let's suppose phi is a rotation of 60 degrees about the origin. Then the group generated by phi is a cyclic group of order what? How do we go about determining this? What is the order of this group? That is to say, if we're taking a cyclic group and we know the generator, phi,
How many times do you have to use actually?
right, we have to take as many powers of phi as it takes to get to iota. Hello? I hung up. I thought it was a question. So right, this is order 6, right? Because 360 divided by n equals 60. What does n equal? 6. Divided by n equal to 60 degrees implies that n is equal to 6. Okay? Or another way to see that is look at our plane again. Rotate this by 60 degrees, well, I don't know how to rotate by exactly 60 degrees, but it takes 6 rotations of 60 degrees to get back to where you started. Okay? Okay. So now let's investigate this a little bit further. This might seem kind of simple, but there's actually a little complexity that we might not have yet realized. Okay, so let's say that rho is a rotation of 36 degrees about the origin. Then the cyclic group generated by rho has order what? Yeah, good, has order 10. Now, can you produce another generator for this same group? That is to say, can I think of something besides rho that also generates a cyclic group of order 10?
Yes.
Okay, here a yes. How do we do that?
Shifted by a certain set amount.
Your intuition is spot on. What do you mean by shift, though?
Like if I start with, instead of starting at like 0 or something,
0 degrees?
yeah, I can just start somewhere else.
Yes, but not just anywhere else.
36 degrees, or specifically.
Okay, this is related to what I'm going to ask you to do tonight. So this is good. This will take some thought, but let me tell you a specific example of what you can do in this case. Okay? Notice that if we set beta equal to rho cubed, okay? So, in other words, what is, somebody explain to me, in terms of the physical geometry, what rho cubed is?
3 rotations. Yeah, so like 3 times the angle.
It's rotation by how many degrees?
Rotation by 108 degrees.
108 degrees, yeah. It's rotation by 108 degrees.
Because it's odd, right?
Almost. It's not a divisor, it's not divided by 2 nor 5. Okay? Notice that if you set beta equal to rho cubed, then the cyclic group generated by rho is equal to the cyclic group generated by beta. And in fact, there's more we can say. The cyclic group generated by rho is equal to the cyclic group generated by rho cubed, i.e. beta, is equal to the cyclic group generated by rho to the 7th, is equal to the cyclic group of generated by rho to the 9th. Okay? So I'm just telling you this, and you're gonna work out how it goes tonight. Okay? So, how are we doing on time? Oh, we got plenty of time. Good. Okay, so here's another fun fact. Notice that all cyclic groups obey the commutative law. The commutative law. That is, if we take alpha and beta elements of the cyclic group generated by gamma, then alpha beta is equal to beta alpha. Okay? Yesterday, I made a kind of a big point of saying we're not guaranteed that arbitrary transformations can be interchanged, right? Why is it the case that in a cyclic group this is always true?
Rotations are commutative.
Ah, yes, but not all cyclic groups are rotations,
Right.
generated by rotations. Also, that's not technically true, by the way.
Rotations about at one point.
They're infinitesimally commutative, but
Oh.
that's a result from differential equations. We won't talk about that.
Right.
So remember, the says, yes, thank you, Jordan. Jordan says they're each powers of the generator, right? Since alpha equals gamma to the n, and beta equals gamma to the m, alpha beta is just gamma n. Sorry, I said that in reverse, but you know what I mean. And so gamma commutes with itself. Any transformation commutes with itself. It doesn't matter,
Yeah.
right?
You can't tell if it's different.
You can't tell the difference, right? This is gamma. Usual rules of exponents apply. Exponent arithmetic. Of course, this is equal to gamma to the m times gamma to the n, or in other words, beta alpha. Great. Good. Okay, so historical note. Commutative groups are often called abelians. In honor of, let me spell this person's name correctly. Niels Heinrich Abel. Okay, so he died at 26 of tuberculosis. But before he died, he was able to resolve a 350-year-old question as to whether or not an arbitrary polynomial can have a closed form solution, right? When you take high school algebra, you're required to memorize the quadratic equation, right? That is to say, you can plug in the coefficients of a quadratic polynomial and get the solutions out.
Oh, right, you prefer 500, yeah.
And it turns out that, in fact, you can do that for cubic equations and quartic equations, which are fourth degree equations. What Abel showed is that there cannot exist a closed form where the solutions of a fifth degree polynomial, of an arbitrary fifth degree polynomial. Okay? Very profound. Kind of a cornerstone of where group theory comes from. Really interesting history. If you're interested, I would highly recommend reading about that. Sorry?
It's the same problem that led to complex analysis.
Yeah, not false. So yeah, it's a profound thing. So don't be confused if you see abelian. Okay. So, at the beginning of today, when we started talking about new content, I told you that we were going to be talking about involutions. Finally, we can say what an involution is. A transformation gamma not equal to iota that has order 2 is called an involution. Okay, that is to say, that is gamma squared is equal to iota. Okay, it may seem,
Does iota already doesn't have order 2, right? It's order 1.
yeah, but okay, so iota satisfies this, right?
Right. Okay.
That's it. That's the reason I say gamma not equal to iota. Okay. So here's this might seem somewhat unmotivated, but here's the rub. Here's why this is interesting. Equivalently, an involution must satisfy gamma is equal to gamma inverse. Okay? So this is a common theme in many branches of algebra. Group theory, representation theory, algebra, these involutions or idempotent things that equal their own inverse, are a key component of classifying different types of structure of a given class. Okay, and that's exactly what we're going to do. We're going to use involutions to help us characterize different transformation groups. Okay? Okay. So, I think we might be a little, actually we might get through 2 heavy examples here. I'm hoping. Okay, so let's suppose, again, that rho is rotation by 90 degrees about the origin. Then the cyclic group generated by rho, we give a special name, C4. C for cyclic group of order 4, right? Just some convenient notation. Then, okay, so I kind of said before that for a cyclic group, we know everything, in a certain sense, once we know the generator. Let's make that explicit. And what do I mean by explicit? Well, what I mean is, let's write out a multiplication table for this group. So I want to know what every element of this group times every other element of this group results in. Okay, I know there's only 4 elements, right? So we have iota, rho, rho squared, and rho cubed. I'll list them again in this column. Okay, so to fill in this table, I just take the column and the row and multiply them together. Iota times iota is iota. Iota times rho is rho. Iota times rho squared is rho squared. Iota times rho cubed is rho cubed, not beta. Okay, so rho times iota is rho. Rho times rho is rho squared. rho times rho cubed, rho times rho squared is rho cubed. And rho times rho cubed is rho to the fourth, which is iota. Okay, so likewise, rho squared, rho cubed, rho squared times rho squared is iota again. Rho squared times rho cubed is rho to the fifth,
For the second.
which is rho to the first.
Right.
Right? So I'll compute this on the side.
Yeah.
Rho squared times rho cubed is rho to the fifth, which is rho to the fourth times rho, right? Which is iota times rho, which is just rho. Okay? Sorry, I keep writing betas. Rho cubed times rho is iota. Rho cubed times rho squared is rho to the fifth, which is just rho. And rho cubed times rho cubed is rho squared. Okay, so it's something I lied to you, right? You can know more about the group, but it all stems from the generator. And that's how we deduce this table.
But nothing there isn't contained here.
That's right. It's contained, but it's not visible. Yeah. Okay, good. So this is called a multiplication table. Or Cayley table. Cayley, after Arthur Cayley, one of the first people to investigate matrices and applying transformation geometry to arbitrary finite dimensions. Very prolific mathematician. Now, there are a lot more interesting groups than just cyclic groups. Okay, so let's investigate another group of order 4, which is not cyclic. Okay, so let me make a definition first. A group may depend on more than one generator simultaneously.
Do you mean like it has more than one, or like not a single one works?
So, what I mean by this, remember, for the cyclic group of order 10, we exhibited 4 different generators. But the group was generated by just one of those at any time. Right? What I'm saying here is that some groups depend on more than one generator at the same time.
Like they can't be generated by a single.
They can't be written as a cyclic group. These groups are called non-cyclic. These groups are non-cyclic. But we use the same notation that is these angle brackets and just parentheses separating transformations is notation for the group generated by alpha, beta, gamma, so on and so forth. Notice I put no restriction on where this ends. There are groups with infinite numbers of generators. We will be primarily concerned with a finite number of generators. Okay?
Compared to linear algebra,
I'm sorry?
to compare to linear algebra, are we thinking of this in the sense that like the product of any power of any number of these is not in the group?
Yeah, that's right. So I was about to say that actually. Good, thank you. The group consists of products of powers of the generators. E.g., you can have alpha squared, beta, gamma, beta, alpha, gamma, whatever combinations you want. What do we want? Gamma cubed.
It's like some weird version of span.
Yeah, but it's not linear.
Right, it's like span, but it's not addition.
Right. Yeah, and there's no scaling here
Well, I
either.
mean, scaling is just addition.
Yes, that's okay for now.
Well, I mean, because when you're scaling that, you can treat it as addition of alpha plus alpha. It's the square, but the addition term from that makes sense.
Yeah, okay.
Four vectors,
Sure.
right?
Yeah, yeah. Think about that some more. We don't have to talk about it right now, though. Okay. So, remember the exercise from yesterday? I asked you to come up with some subsets that were not subgroups. You can always take a subset and generate a subgroup. You just take all the elements of the subset and put them in angle brackets and see what group you get. Okay? It's very hard, in general, if you're given an arbitrary group, to come up with generators. Okay? We won't talk about that problem much because we're interested in very specific groups that have geometric motivation. But yeah, this is just to give you a taste of how large the field of group theory is and bizarre it can become. Okay, so now that we understand a little bit more about how groups can be generated, let's try to discuss another group of order 4. So, example, consider the following transformations. Okay, so sigma, so O of x comma y equal to negative x, negative y, sigma sub h of x comma y equal to x comma negative y, and sigma sub v comma y equal to negative x comma y. So let me just say that together with iota, these form a group. Yeah, these are all certain types of reflections, right? Good. So let's write out the multiplication table for this group, okay? And also, this group is called V4. I forget what V is for. I think it was discovered by Felix Klein, or studied first by Felix Klein. But I don't remember what V is for. Probably something German. Okay, so anyway, let's write out the multiplication table for this. So again, we have iota. How did I write this? Sigma H, sigma V, sigma O, I, sigma H, sigma V, sigma O. Okay, so iota, iota, you got iota. Of course, my first row, since iota acts trivially, I just get top row again. Okay, so sigma H. Now, what's sigma H times sigma H? Iota, right? Because if we apply sigma H once, we flip y negative. If we apply sigma H again, we flip it.
It's an involution.
It's an involution. Yes. Good. So we get iota. Spencer says, I think the V stands for, my German's terrible, Viergruppe, which means four group. And it was Klein, right, Spencer? The Klein 4 group, I think that's right. Thank you for that. Good. I should know my history better. Okay, so what's sigma H times sigma V? Sigma O, yeah. And sigma H, sigma O is sigma V. Right? And I might be going through this a little fast, but where I'm just applying each of these three definitions at each stage. Okay, so, we're almost out of time. So we'll finish filling this out tomorrow and then compare C4 and V4. But let me quickly tell you some homework exercises that I would like you to think about before tomorrow. 2.4, 2.5, 2.6, 2.9, and 2.13. And I will put an announcement on Canvas reiterating those exercises later this afternoon. Okay, so sorry we ran out of time. I really wanted to get to the comparison of C4 and V4. But we'll talk about that tomorrow. Have a good afternoon. Yeah. Yeah. See you tomorrow.